Okay, we're going to finish up the decomposition water lab. So we've let this go for about 20 minutes. And you can see that obviously one test tube has a lot more gas collected than the other test tube. The formula for water is H2O. So you should have, when you break down each water molecule you break down, you should get 2 hydrogens for every 1 oxygen. And so the hydrogen is collecting in this test tube. The oxygen is collecting over here. Oxygen has a tendency to what we call oxidize metal. Okay, and so it's breaking down the electrodes. So you can see that this water here is has a lot more, I guess you could say, junk in it. This looks very, very clean. Okay, so in this one we have hydrogen, and this one we have oxygen. So we're going to mark those with a rubber band. First of all, I'm going to unhook all this. Then we're going to mark the water levels with a rubber band. And we're just going to let the water pour out of there. And we're going to fill the test tube up to the rubber band mark. And now we can measure the amount of gas we have by pouring that into a graduated cylinder. So I've got these 10 cubic centimeter graduated cylinders. I don't think it's going to be more than 10, but no, it's not. And so the one with hydrogen in it is 6.4. So let me write that down. And the one with oxygen in it get some of that junk out of there. It's almost 3. I'm just going to call it 3. And so it tells you here, if I can find it, it says divide the volume of the hydrogen by the volume of the oxygen. So let's go up to the front. And we can do that up here. And so we're going to find 2 ratios. The first ratio is the volume ratio. So the volume ratio is equal to volume of H divided by volume of O. So for us, the volume ratio is 6.4 divided by 3. Which is 2.1. So the volume ratio is 2.1. If we did it correctly, which is hard to get exactly 2, but we should get 2. Should get twice as much hydrogen as oxygen. Now, our problem was the oxygen was breaking down some of the metal, so not all the oxygen was going into the top of the test tube, I guess we could say. Then the first blue question says, does the amount of solution added to the water affect the volume ratio? Well, we didn't get a chance to see that here, but every group is going to have a different concentration of sodium carbonate solution, the stuff in the beaker. But what you should find is you're always going to get a volume ratio of 2. It doesn't matter. Okay, anything If we don't get 2, it's because of a mistake that we made. Then it says using table 3.1, what's the mass ratio? Well, the mass ratio is going to be the same. We're going to say, not the same number, but calculate the same way. So mass ratio is equal to mass of H divided by mass of O. But we've got to figure out the mass of H and the mass of O. And the way that we're going to do that is use some stuff from last semester. We'll use this equation. Mass is equal to volume times density. So for H, it's going to be mass is equal to 6.4 times the density, which you can look up on the internet. But it's just this number, 0.00084. And so the mass of H that we have is 0.0005, I'm going to round this, 54 grams. So we definitely couldn't mass that on a tropline balance. So a better way to do it is to calculate it. And then for O, mass is going to be 3 times 0.0013. So if you do the math there, 3 times 0.0013 is 0.0039 grams. Then we can plug that into this. We can say mass ratio is equal to 0.00054 grams divided by 0.0039 grams, and you get a mass ratio of 0.14. Okay, and what it should be, I'll put down here, should be 0.13. So we're very, very close. This down here should be 2. So I'll put stars beside that. So we know that we're off by a little bit, but those are very, very close to what they actually should be. So in other words, even though you've got, this is just telling you that you've got twice as much hydrogen as oxygen. But since hydrogen has such a small mass, even though you've got twice as much, twice as many atoms, the mass of oxygen is so much more that you get a mass ratio of 0.13. So there's 0.13 grams of hydrogen for every 1 gram of oxygen, even though there's 2 hydrogen atoms for every 1 hydrogen atom, or 2 cubic centimeters of hydrogen for every 1 cubic centimeter of oxygen.